Hi everyone, both here in Canberra and online. We're just getting ourselves organised here. I think we're now ready to get going. So first of all, welcome and thanks so much for joining us, either in person here or online. I'd like to begin by acknowledging the Ngunnawal people as the custodians of the land upon which we're meeting here today and on which our fellows work here in Canberra and live and apply our science and technology and engineering. And I pay my respects to their elders past and present and to any Aboriginal and Torres Strait Islander people who are joining this meeting. And of course, noting we've got people online from around the country, I'm sure that you pay your respects to the custodians of the land on which you're attending today. So for those of you who don't know me, I'm Helen Clue. I'm the chair of ATSE's ACT Division Committee, and I also hold an honorary professor role at the University of New South Wales. Before I retired a few years ago, I worked in CSIRO as an atmospheric and climate scientist, and I led much of CSIRO's work in that area in the decade from around 2010 to 2020. And I'm honoured to have worked closely with both of our speakers today over the course of my career. And so welcome to the first of these hybrid seminars for 2025, which the ACT Division Committee run. This year, we're going to have a bit of a focus on some of the big challenges around global change, including climate change, but not only climate change. Talk about polycrises coming together, reinforcing each other, and challenging our ability to form solutions and inform decision making. The issues that we're considering this year around water, carbon, climate change, electricity, etc., are issues that demand a strong scientific basis, as I know you all know, and they need science, technology, and engineering to identify and implement solutions. So they're therefore issues that are critical to ATSE's mission. Today's seminar, focusing on the global carbon budget and Australia's role, sets the scene. And we really are so fortunate today to have two expert and distinguished speakers to explain the science to us, covering the carbon cycle, carbon budgets, emissions, their link to climate, and how this can be translated into policy outcomes for Australia and decisions that Australia has to make, along with some of the current research and technological challenges that we have to face and address if we are to meet this grand challenge. The way that we'll proceed today is we'll start with Pep's presentation. Pep will speak to us for around 20 minutes or so, and I'll ask you to hold your questions because the two talks, so we'll go second. The two talks are quite closely linked. In fact, our two speakers have worked together to ensure that it's a nice, coherent, integrated presentation. So if you could hold your questions to after the second talk by Will, that would be great. We hope to finish by around 1:30, 1:40, so that'll give us lots of time for questions and discussion. If you're joining us online, we really want you to be involved as well. So please enter your questions that you have into the Q&A, which you should be able to find on your Zoom screen. And we'll take those questions at the end as well. Okay, let's get on to the first presentation from Pep. I'm sure many of you have gone and looked at his bio, but let me begin by introducing Pep. He's a Chief Research Scientist with CSIRO, and he's the Executive Director of the Global Carbon Project. This is a global consortium of scientists from around the world. He's also a lead scientist with the National Environmental Science Program, or NESP for short. They have several hubs, and he's a lead scientist in their Climate Systems Hub. Pep completed his PhD in biology and terrestrial ecology in Spain, and then he went on to hold several positions in the US before moving to CSIRO. I can't remember which year, but it was a while ago. Pep's collaborative and highly integrative research develops budgets and trend analyses of all of the major greenhouse gases, and this work is done at scales that go from local to regional to global. His research, as you'll see today, has assessed the size and the vulnerability of all of Earth's carbon sinks and pools. He's advanced, or the research has advanced our knowledge of carbon climate feedbacks. It's contributed to quantifying pathways to net zero emissions, and that includes especially the role of land-based carbon sequestration and negative emissions. And he uses this robust scientific understanding that he's developed with his colleagues and collaboratively to inform policies and actions to mitigate climate change, again, at levels that go from national to global. It includes contributions to the Intergovernmental Panel on Climate Change, who every 7 years or so produce their assessment reports. And I think Pep has been involved in those for the last 18 years, which covers 3 assessment reports, the 4th, the 5th and the 6th, for those who follow them closely. And I do understand that Pep's involved in the 7th assessment report, which is being formulated as we speak. He is a fellow of the American Geophysical Union and our own ATSE. And he's been recognised as one of the world's most influential and highly cited climate scientists. And apart from all of that, he's a terrific communicator and a very willing communicator on media and to audience such as ours. So Pep, welcome to our seminar, and you'll be speaking on the global carbon budget and emerging risks. Over to you. Thank you.
Thank you, Helen, and thanks for the invitation. Thanks for everyone for your interest, both online and here. As we said, I'll do the global, which is the easy stuff, the hard stuff on Australia. So, and let me just begin by saying that carbon budgets means very different things to different communities, and we need all these communities to actually ultimately be able to produce the ultimate policy carbon budget, which is how much more we can emit before we reach or avoid a particular threshold or target global mean temperature. That's from a global point of view, then obviously needs to be translated into the national level. So I want to start with this, what we call a carbon budget, which is all sources and sinks, anthropogenic and natural. And the reason this is important is because you see in red, the big direct human impact. But that direct human impact has an impact on the atmospheric composition, has an impact on the climate, rainfall, the temperature, which then impacts the site errors, which are the natural sources and sinks. And that's actually quite significant in the sense that those natural sink changes have huge influence as well in the net carbon balance of the atmosphere, and therefore the size of the problem that we have and that we need to deal with. Just to illustrate this thing, next one. So what you see here is actually the cumulative CO2 emissions from burning fossil fuels and doing deforestation around the world since 1850, and the impact that it had in the atmosphere. So, we're starting at 2,000 plus parts per million, 200 parts per million, and then we go 100 more, from all the combustions of coal, and then we go, 81 more from all the gas, and so all the way to what basically is enough CO2 emissions to reach 620 parts per million. Next one. But we're not at 620. We were at 419, 222 last year, which basically means that we have this humongous response of the Earth system to that human perturbation, which removes almost half of all concentrations. And so the reason I'm showing this thing, and I'm going to talk about a little more now, it's because we always think about what humans are doing. But humans are doing the direct thing that we have a control with in terms of how much we combust and how much we deforest. But then we have all the response of the planetary system, which is in response to that direct impact, but that we need to understand equally to be able to finally put a budget together. Next one. So what I'm showing here, and that's where we're going to try to dive a little more into this natural CO2 sink. So what you think here is, first of all, the red line. It's basically emissions from fossil fuels and land use change going up always. It's non-stop 1 minute and continues to go up still, since still last year. And then the dot points, it's what we call the airborne fraction. That is the percentage of all emissions from our anthropogenic emissions from our activities that stays in the atmosphere. So which basically implies that if not 100% stays in the atmosphere, a fraction has been taken away by those oceans and land sinks. And there are two remarkable things of this figure, which we're learning a lot, which then we move into the modeling. And that is, first, over the last 60 years, the mean value of this, how much stays in the atmosphere, has largely remained constant, at about a little more than less than 50%, 44 in there. That's remarkable. That means that in the 60s, when we're emitting 6 billion tons of CO2, 3 billion tons were taken away by the sinks. Now we emit 42 billion tons, 21 billion tons are removed. I mean, that's extraordinary and just shows how much of a climate change discount we have, 50% discount, as a matter of fact, thanks to the behavior and this kind of nature services. The other remarkable point of this figure is the fact that these things are incredibly sensitive to something. They go absolutely crazy from one year to another. I mean, you have years where you are living in the atmosphere up to 80% of all emissions you put, and other years that you're living barely 20%. So the key thing is to really understand these sensitivities and try to see what we can bring into the modeling. So next one very simple thing that we do is to test all these against the single biggest climate mode of the planet, which is the El Nino Southern Oscillation. So the red shadow means El Nino, blue, La Nina. So next one. So when we have an El Nino, which is temperatures globally above average, we have the sinks perform very poorly. So the fraction of the total emissions stay in the atmosphere are well above the average. Next one. When there's a La Nina, the temperature of the globe is cooler than the average, and we have a much better performance and efficiency of the sinks. And then it's still really interesting to see that there's still a lot of years where the sinks are doing pretty well, but they're not a La Nina year either. So if you press next, those years happen to be years where we had major volcanic eruptions with major influx of aerosols into the high troposphere, lower stratosphere, cooling the planet. And again, a cooler planet meaning a better efficiency of these carbon sinks. So we know that from a trend of where we're traveling to a more warming world. And so we're traveling more to efficiencies, which are expected to decline over the years. So that's very important. And we put this information and other information to do the next budgets. Next one. So this is the entire budget, how much carbon is in the land, goes into the ocean, and how much is into the atmosphere. Into the atmosphere means the emissions that we can put into the atmosphere for each of these measure family of the scenarios that we use in the IPCC, anywhere from the 1.5 that we want in the Paris Agreement all the way to more than 4 degrees, which of course will be a different world that we don't want to know about it. The CO2 sinks, the natural CO2 sinks, the color components of the bottom, they grow a little, and we think that will continue to grow in response mostly to more and more CO2 in the atmosphere. Next one. But here's the dramatic story and the punchline of the story is that when you put all the CO2 that we can allow for every single of these scenarios, the full budget, oceans, land, and all the emissions in the atmosphere. So we have that from 1850 to 2100, we find that if we stay low in the temperature range, nature helps us dramatically, as much as 78%, 60% of removing emissions. While as you move to a hotter world, basically, for the same effort, ultimately trying to go back to it, you have all the extra emissions that you put together, plus all the extra emissions that nature didn't do removal for you. So this is the most compelling statement per se that we really want to be at the early end of temperatures, not just to avoid what we don't want in terms of impacts, but even just from an economic point of view, resolving the problem. If we're going to resolve it, you better resolve it now when you have this huge help from nature, not later on. Next one. All right, so we go and we do this incredible, quasi-linear relationship between the cumulative CO2 that we have emitted since 1850 and the excess temperature in the climate. And we get this almost quasi-linear relationship where you can say, well, we spend now 2,600 gigatons, billion tons of carbon dioxide, and that gave us about 1.2 degrees excess CO2. And by doing that, you can now move on into the line up and just make a decision as where you want to stop, what's the equivalent of the amount of carbon that you can put. And so next one, so there's a huge diversity of things. So we went and we tried to do something a little fancier than that I was just telling you about putting a line in. And it's to come up with a relationship between cumulative CO2 emissions only and the temperature that CO2 has incurred, leaving aside all the other greenhouse gases, all the aerosols, everything that also has an influence in the temperature of the globe. And then, next one, we begin to do a careful reducing the sink from what would be the initial sink, which is, initial carbon budget, the red rectangle, which it's incorrect because this is only CO2, and we want to stop at the temperature at the top left. So we need to, next one, we need to remove per every of these scenarios, all that carbon that we need to leave a space for other non-CO2 gases and what we call the warming commitment at zero, which basically means that when you're at reach zero, you still have a little more warming going on, a Q. So we need to keep reducing the carbon budget, the CO2 carbon budget to become smaller so we leave a space for all those other gases, depending what they do. The next one. And then we still to further reduce that budget because we know that our models do not account for a lot of important Earth systems. Earth system processes and carbon climate feedbacks. We know some of the things work, but we don't quite just put these things into the models yet. And one example, next one, is that for the first time, the budgets I'm going to show you actually have embedded now. We have removed a bunch of carbon as what we think we know best, which of course has huge uncertainties, which is the permafrost CO2 methane climate feedbacks. So that those budgets now, they're being shrunk, so allow, for some of these emissions to come. Now, we might not know this thing very well, but this is the state of the knowledge as per the day we put these budgets. Next one. So that's the budget. Basically, the gray dark means everything that we have emitted already, and the little kind of slice of pie that comes out at the top, it's what we still can emit. And so if you look at the 1.5, given the emissions in 2024, about 42 billion tons of carbon, if we were to stay constant, which so far we have not stayed constant, we have gone up all the time, we would have 6 years to go. And if you want to go to 2 degrees, you have 27 years. Now, these are the budgets, the geophysical budgets. Doesn't mean that that's the budget that we're going to create for us as a society to kind of go down to zero and beyond. So next one, it shows the budget. Basically, the budget means all those 3 figures that I showed a second ago. So now have one of these lines. And so before I said there's 6 years to go to 1.5, that is the end of this decade. But now I push the line of the 1.5 to 2036. Why push that? It's because we're no longer staying at the same CO2 emissions of 42 million gigatons, of 42 billion tons of carbon every year, which is now coming down very quickly to reach a net zero emissions, which a net zero emissions, by the way, it's a geophysical requirement of the system to stop further warming. And the reason is a geophysical requirement is because CO2 stays in the atmosphere forever. It just it goes down, but at 10,000 years, you still have more than 10% of all the emissions you put, 10,000 years. So let alone, the next 100 years. So you really have to go to zero. It doesn't matter whether you put in 42 billion or you put 1 billion. You are having a huge residual in the atmosphere, and therefore you're going to have more warming. So all of a sudden now we have expanded the budgets just by, kind of going down at not at the same speed of emissions, but an insane amount of decline, which is an impossibility. So these declines are not good either for transforming society and the economies. But these are the geophysical statements that we must do so we understand that anything beyond that is humans deciding how we do the accounting. And that's the next one that takes us to the next one. And the next one is that we have created this thing of the negative emissions. Negative emissions means that we'll create technology that will take CO2 from the atmosphere, which allow us to basically expand the carbon budget as much as we want, as long as we believe that later on, after we reach net zero emissions, we can take the entire planet not to be a source of CO2, but to actually be a sink of CO2, the whole planet to be a sink of CO2 so that we can begin to repay the carbon credit we took the previous 30 years because we realized that we didn't have time to do it in an economical, sensible way. That's what some people call, using the credit card of your children and your grandchildren, to pay for the fact that we didn't get our together before. Now, having said that, we are embracing these negative technologies, as crazy as it might sound, because we will need not just to kind of go to net zero, but to really take CO2 from the atmosphere, just for the mere fact that, it has taken us 30 years to talk about what to do, and now we just begin to do things. Next. So how much of negative emissions we are already doing? Because it's not that we need to wait to 2050 to do negative emissions. That needs to start right away, at the same time as the mitigation and reduction of emissions, which is, of course, the priority. And then at the same time, begin all these negative emission technologies. So at this point, we're doing quite a bit of reforestation, and not for climate change, by the way. The single biggest contributor is China, which they've done it just to stop the desert of, engulfing Beijing and other major mega cities. But nevertheless, those trees were not there when we started. Now they're there, and they're sucking up a lot of CO2. So if you do next, you'll see it's 5%, equivalent 5% of all fossil fuels. So that's actually something very significant. Now, how far we can take this thing? Remember that deforestation kind of gets to a plateau, and then they're not sucking up much more. They just are in a balanced exchange of CO2. But then you need to keep planting. How much we can do that forever? So there are limits. And then the rest, the kind of newer technologies, were just at the beginning, which it means are contributing nothing, but not to say that any new technology will start from nothing, and hopefully will grow as much as we can. Next one. So I do just want to give you an example of a very mature technology and industry just running, which is in Iceland. The reason why they put this thing in Iceland is because there's free geothermal renewable energy for as much as you want. Putting this process of sucking up CO2 from the atmosphere takes a lot of energy. So this is kind of the ideal place in the world to do it. Anything else is going to cost us more dear to really get the energy to do it. But just I want to show you the next one. It just shows that, basically the system, it's a sizable industrial system. It takes about 4,000, tons of CO2 every year. There's speculation that it didn't tell us the price, but whether some of the big corporations are beginning to pay in between $500 and $1,000 per ton. But the point I'm trying to make is that in order to just develop an industry that could take half of the negative emissions we need to do, which is about minimum 10 billion tons, we would need 1,250,000 of these plants around the world. And the reason I'm making this statement is not because forget about it, that's not good, we will never reach it. No, we will never reach it. We've never done an industrial development that would be able to develop a million of these things. Just for you to know, we have 3,000, not even 3,000 coal power plants around. We had more, we had 9,000, but we're shutting down very quickly nowadays. But the point being that that we will need a lot of new technologies to basically support this removal of CO2 above and beyond how far this particular industry can go and how cheaper this particular industry can go. Thanks. And so this is really a statement, actually a statement for particularly ATSE as the kind of engineering component of sciences, is that we need a lot of different technologies, not just in the carbon space or CO2 space, but on the methane space. There's just, really great ideas, a lot of chemistry involved as to how we could really, take CO2 and methane. In the case of methane, probably take methane and transform it into CO2, which is a much, less powerful greenhouse gas. But the idea is that we do need, particularly at the industry level, quite a bit of development of new ideas and technologies to really kind of bring this thing down to a level that could potentially make a little sense. So just to kind of really place that, from an ATSE point of view, I mean, not just the negative emissions, but also the reduction of emissions, particularly all the things that we cannot electrify, which are growing very quickly, all the space that we can electrify, clearly we need still a lot of support of research and development, and actually really is at the forefront. Next one. And so this is my just last one, just as a segue to Will. And just to say that I talked about the global carbon budget, and clearly the global carbon budget means nothing to anyone, certainly not to the governments of the world. So you need to take that budget and basically share the cake with everyone. And just to make the point that from a UN perspective, the Climate Change Convention, there is no legally binding anything that would make you to have a particular piece of the cake, bigger or smaller. It's all, as we know, the Paris Agreement is all voluntary. And the only thing that the convention says is this statement here, which says agreement will be implemented to reflect equity and the principle of common but differentiated responsibilities and respective capabilities in the light of different national circumstances. Translated, meaning if you're a rich country, you need to do more than what we expect to do globally as a mean value. So if we say we want to stop 1.5, and we need net zero emissions by 2050, 50% probability means that Australia as a rich country clearly needs to kind of stop, before 2050. If you are Ethiopia, you may go to 2060. That's the intent of this sentence. The only thing that binds you to do anything other than everything else is voluntary from their perspective. So just one more click and we're done. Just to say that, of course, scientists have run and they, made a lot of numerical decisions about how we could share these things. This is just scientists playing with numbers. And of course, you can do it proportional to current emissions, so you don't give a shock to the country emissions. You let them kind of go and then curve slowly. You can say, well, we should have a global equity here and just go all equal per capita, divided by per capita, and depending how many people you are. And you can just go on. And of course, at the end, you have all the ethics and all the economics that enter, which is what ultimately countries are making decisions upon. So I'll stop here, and that's perfect place for Will to come over.
Please, Will, before we get started. Yep, you can come up here. Will, sorry. So we'll now sort of take over and take a more of a national perspective, I think. So his presentation is entitled Emissions Trajectories, Glide Paths and Budgets. Well, slightly shortened on the screen now.
I forgot what the title.
That's all right. It's no drama. To introduce Will, he's currently the lead scientist with the Australian Government's Climate Change Authority, as you will have read, who work across climate science, emissions reduction, carbon removal, adaptation, oceans and other climate policy issues. Climate Change Authority has been in the news a bit. It is an important organisation for Australia, providing that independent oversight. Will comes into this role with a PhD in geological sciences from Brown University in the US. He worked in the US as a research fellow, a postdoc at Columbia University, and then in oceanography in Woods Hole. place well known to oceanographers in the US. And then he moved to Australia, where he joined the CRC, the Antarctic Climate and Ecosystems CRC. As a researcher, he directed the Sedimentary Basin Management Initiative at the University of Melbourne. He's worked extensively at that interface between science and policy. I think I first started working with Will when he was, I think it was when you were in the Department of Climate Change and all of its predecessors. But he's also been in the Office of the Chief Scientist for 7 years, from 2010 to 2017, serving as the head scientist there, or the head of science. I then took on a role as the lead climate scientist at the Department of Agriculture, Water and the Environment before moving on to the Climate Change Authority. And I just finished by noting that both Will and Pep are actually members of the Australian Academy of Sciences, so our sister academy, their National Committee for Earth System Science. So Will, over to you. Thank you.
So much. Thanks, Helen. And let me say it's really an honor to be here. So thank you for asking me to give this talk, and it's an honor to share the talking privileges with Pep. And we've worked together on a few things for a while. So let me just take that and take it. I'm going to have a few common touch points, but take it in a little bit of a different direction. So if I could just quickly have the first slide. I just want to add the Climate Change Authority's acknowledgement of Indigenous Australians as well here, and everyone who's online. And you could give me the next slide next. One of the things that we find going around and giving talks like this is that people don't know who and what the Climate Change Authority is. So I always add a few slides like this just to give a sense of what and who we are and what we do. And we are an independent agency. We work within, you might say, the environment portfolio, but we work across the whole government. And we have an independent chair and board. We have a secretariat based in Canberra and other places of about 65 people. We have some statutory responsibilities to review the NGERS legislation, which includes the Safeguard and the ACCU scheme. We provide an annual progress report to the government every year, annual. And we occasionally take on writing of reports that are either self-initiated, and the year before last, we did one on carbon sequestration, broadly considered, which Pep just alluded to. And that was a self-initiated one. And we recently released a report on the implications of nuclear energy in the grid. That was a self-initiated report. And occasionally Parliament can request, or the minister can request work from us. And our sector pathways report was an example of a report that was requested of us. So those are the kind of things that we do. And next slide, please. And just to give you an idea again, that who we are is, and I have to change this now because it's already out of date, has Kathy Foley as the chief scientist, as an ex officio member. And of course, Tony Emit, well known to you at ATSE, is now the chief scientist. And in that role, will join the Climate Change Authority as a member. So the next slide, please. And the things that we're working on now is our targets advice. That's the other big piece, and that's the big part of our responsibility, is to advise the government on its next NDC, which will include the next interim target, the 2035 target. We're in the midst of doing all the background and the underlying analyses to let us formulate that. Of course, we just released a report on nuclear energy. We will be, we're doing some work on understanding the electricity system as a whole that we'll be working on over the next few months. And of course, our annual progress report sometime toward the end of the year. So those are the things we're working on now. Can I get the next slide, please? And I want to just come back to that NDC piece, because we've just seen examples of how you could think about a carbon budget. And we've seen examples of, through IPCC scenarios, pathways, time-dependent pathways into that. And one of the things that I want to make clear, we always make clear, is that we're, of course, thinking about what pathways might look like through time. We think about what a budget might look like, but of course, we have all these other considerations that go to the well-being of our communities in general, their economic and social well-being, and the opportunities and risks to the economy of the kind of transition that we're going to. Part of that is because we are charged with advising, I'll say this, we advise on the risks of climate change, but also the opportunities and risks of transition. So it's that 360-degree view. That means that we, in formulating our advice, we take a much broader set of considerations into account when we formulate our advice on, let's say, a point in time target, which looks like a one single number X% by whatever year. But in reality, it's taking all those things into consideration. Next slide, please. So I want to go back and I want to touch upon one way of thinking about the budget. So Pep showed us a global carbon budget, and that again is all the sources and sinks, both natural and anthropogenic, and this one doesn't show that, but in many cases we think about the size of the reservoir. The ocean, for example, is a very large reservoir of dissolved carbon. And this is one that was an attempt to assess Australia's carbon budget done by Pep's team and published in Global Biogeochemical Cycles the year before last. But one of the things I've circled in red there, the anthropogenic components, and these are the things that we look at and try to assess in the context of our inventory. But there's another piece, what I've circled there, put a thing in green around that, that Pep also pointed to, and that is that land sink. And again, that's just Australia, but of course there's a global land sink. And one of the challenges is actually understanding the interactions and trying to separate the roles of that natural sink, which again has all that sensitivity and feedback into climate variability, with some of the components of that land sink. So land use change. So a pretty big challenge. And part of what I want to do today is to challenge ATSE, because I think ATSE has a really big role in helping unpick some of these really thorny questions about climate policy. And I think that's one of the big ones. But so that is a way of thinking about a carbon budget. Next slide, please. But the other way, and again, another touch point is, and Pep's just showed this, again, this idea that the cumulative emissions, again, because CO2 has such a long tail due to the uptake mechanisms, the initial few centuries of ocean, mainly ocean and land taking up. Then ocean has a chemical adjustment, which has got a millennial time scale. Ocean then has a sedimentary adjustment, which is more millennia. And then finally, weathering takes up the rest, but it's got an extremely long tail. So CO2 effectively is forever on a policy timescale. Next slide, please. And so again, that's good. And so again, the Global Carbon Project has formulated the idea of a budget. But a couple of important distinctions, and I just want to repeat that. This is for CO2. This formulation is for CO2 only. We need to think about all of the greenhouse gases, and it only works for CO2, again, because of that long life cycle. And it does, but it does provide us with a really simple and understandable metric and a rubric for thinking about climate policy, in the sense that we can move up that diagonal line, and we can move down it through removal technologies and emissions reductions. So that's simple, but it does take away some pieces of information. So there's a trade-off. There's always a price for thinking about something one way. So next slide, please. So the other way of thinking about it, and everyone probably seen this slide forever, and Pep showed a version of it as well. Again, from IPCC, which showed that you have to reduce emissions. You're not going to get all emissions to zero in any foreseeable time frame. So you have to think about what the task is to remove CO2. And as soon as any policymaker or politician or scientist says net zero, they are implicitly talking about removal, whether they realize it or not. And that point about going to net negative is important in a couple of different ways. One, it does mean we have to scale up removals, but also scale them up in a durable way. And so one of the things you see there is CDR on managed land. And you can kind of see that orange line underneath the zero line. So it kind of goes along, and it's saying that the presumption here is that we need to maintain that, but it's not so straightforward to get it to a much greater scale. And some of that is because of the fundamental characteristics of these ecosystems. Carbon has a finite lifetime inside of an ecosystem, and it's cycling. So it's stored, but of course it's got this net set of fluxes. So the implicit message of a figure like this is coming from that yellow edge at the very bottom, which is saying other, it's kind of like other CO2 removals, and it's that other bit that coupled with durable storage essentially back into geology, that is what has to scale up a lot in order to meet the constraints of a figure like this. And that's a huge challenge. And you can kind of see that, no one quite knows exactly what that's going to look like, but we do know it has to scale up from effectively zero to something quite a bit bigger. And two reasons for that. One is to account for the fact that there's a good chance and there's a risk that we will overshoot some of those goals. So there's a good chance at present, there is some risk that we will go above 1.5, and then we may want to come back. And to do that, you need negative emissions. You have to net remove, but also as we go forward in time, the behavior of those sinks, the ocean and those terrestrial ecosystems, if we're successful and really reduce emissions, some of them may turn around and become net sinks. So we'll have to remove more. So that's a key part of this. Have the next slide, please. So that's a time-dependent pathway. And you'll notice that I actually took off all the numbers in the middle on the x-axis, because it's just now between 2100. But I wanted to make the point that to some extent, it doesn't matter whether you say 2040 or 2050 or 2060, the constraints are the same of getting to net zero. And then the area under that, if you think of what the area is, that is a budget. So that's the integrated amount of CO2 that you could emit and still meet the constraints of this kind of a pathway. So I want to start just showing these kind of pictures to say we can make this duality. And I'm going to be just slightly coy and not putting a number on that. That is because we are still in the process of formulating our own advice and what numbers that might include. So if it seems like I'm being a little cagey and coy, that's because I am. Next slide, please. So one of the things that you do lose if you say, here's a budget and you can only spend that much budget. And it's a very powerful metric. It's a very powerful rubric to think about for policymakers and industry and everyone. But we live in a system in which there are time dependencies with multiple timescales. And so we can think about different pathways to net zero. If you could formulate a range of different pathways that might have the same cumulative emissions or budget, the area under them. If you go to the next slide. Again, I've done a very sophisticated thing here. I just used PowerPoint to fill in. So that was, the amount of computing power that took was enormous. It took me maybe, 4 or 5 minutes at my skill with PowerPoint. But all of those have implications in terms of the budget, but each of them has different implications in terms of the time dependencies and the path dependencies of the systems that we're talking about. We have fast responses within the climate system. Things like clouds and other feedbacks, rainfall patterns probably have relatively rapid responses, but we have other parts of the climate system that have very long time scales, things like ice sheets, things like the buffering capacity within the ocean, and the flip side of that buffering, which is the acidification of the ocean. Things that may take a while and then suddenly respond, like these permafrost reservoirs in boreal systems. So the shape of the pathways actually matters. And I want to get that point across too. And that's something you don't quite pick up if you just say a budget. Similarly, if you think about, like a lot of us have been looking at climate risks and impacts through the window of global warming, which again gives you that simplicity and lets you get away from worrying about which model is hot and which model is cool. But it does take away some of that path dependency. And those are two worlds that I think we remain challenged to bridge. Next slide, please. So you can take any shape, and we developed this a couple of years ago to try to give the idea that we can look at our history, extrapolate it forward. We can think about what different trajectories might look like. We call them glide paths because economically we're trying to bring this economy into decarbonization and actually have it land, not crash. So that's one of the things that we're balancing, and that's why we call it a glide path. And again, that's part of the challenge. But any of those can be expressed as a budget. Next one, please. Same here. We looked at in our annual pros report. We said, well, here's what we've done so far. The black dash line is an extrapolation of the emissions trajectory from where it peaked in about 2008. We sort of said, where would that go to? Then we said, okay, what does a straight line look like from now, a couple of years ago, to 2050? Next slide, please. So again, that integral, if you think of it in budget terms, where we've been over that time frame, we emitted net about 10.6 gigatons of CO2. So you can think of that as, if we have a budget, that's how much we spent so far. And what we have left depends on what kind of a trajectory we want to draw. So the bottom there shows a straight trajectory from basically where we are now to 2050. So the area under that can be thought of as budget. The other one is an extrapolation. Again, the area that extrapolated out also implies a budget, but a larger budget. Next slide, please. So this is kind of where we are as a nation. Pep showed a sort of global view of, in his case, he showed the emissions from different fossil fuel sources and land use. We're taking some of that, but taking a sectoral approach and saying, where are our emissions coming from? You can see that the single biggest source, of course, is electricity. We use coal and gas to generate electricity, even though that's about a little over a third of our emissions. It's the biggest single part of our emissions. Transport, industry, others. And then we have that big thing called LULUCF, land use change and forestry, and that's taking up a lot of that for us. In fact, if you go back to that green curve that I showed in the previous slide, a big part of that green curve to the left is actually due to that component. If you look at other sectors, in the net, they haven't seen a lot of change. Electricity's gone down because we've seen the replacement of coal-fired power with some combination of renewables, a little bit of gas, which are lower zero or lower emissions intensity power sources, but sectors like transport have gone up. So we're taking some credit. Next one, please. We're getting a lot of credit out of that piece. And again, it's not easy to know how it's going to behave in the future. So those feedbacks into that system are difficult to anticipate and hard to know about. And I'm going to come to agriculture in just a moment. If you go to the next slide, please. So we did some sector-based modeling for our sector pathways report. And I just show two examples, two main scenarios that we focused on. One is called A50. It just means Australia gets net zero in 2050, and it's roughly aligned, not exactly aligned, but it's meant to be aiming toward what we might do in a 2-degree pathway world. The one on the right is, again, what we might do in a 1.5 world and get to net zero in 2040. And a couple of things about that you can see. One is that you can see that green, you can see the green and sort of purplish color, whatever that color is under the zero. That is what happens to the land sector under these two scenarios in the model. I always stress that this is in the model. Whether this has any relationship to reality remains to be seen. But the model pushes that. And the other thing that the model does is, you see that little purple bit at the very bottom, that's engineered things like direct air capture, enhanced rock weathering, and technologies like that. But the model had no way of incorporating those because it's run internally, essentially by implicit price. And because we don't yet have an easy way of knowing how those technologies scale with price, effectively, that had to be prescribed in the model. So that's a little secret that's hiding in plain sight in the model. And so that's one of the challenges, is how do you anticipate the scale of technologies that are in such an early stage that, as Pep showed, they're effectively zero. And the other one is, again, how do you anticipate the ability to scale land sector removals? Again, this model really just almost forces the issue because it's driven by this kind of a price. So that's a real challenge for how to anticipate and model those things. The other sector I really want to point to is the ag sector. One of the things you see, I don't remember which color it is. Ag, it's kind of a dark green color, the second thing down. One of the things you see, for example, you look at electricity. In both of those, electricity goes essentially to zero. Other sectors go to very low emissions. Ag stays pretty much the same. And that's a massive challenge to get agriculture to zero or even lower emissions. So it's a very it's a very challenging space, and I think that's and as we pointed out in our sector pathways report, that's one that's going to take like a lot of work to get through to a sustained path to decarbonization. Can I go to the next one? And just again, I wanted to point out that any of these can be viewed in terms of a carbon budget. Not only can the whole, in this case, the representation of the whole economy by this sector pathways model, and it isn't the whole economy, but it captures, most of it enough to be a useful representation. All of these can be thought of in budget terms, but again, there's a couple things hiding in plain sight here. One is we can think about a budget for different sectors. And that's an implication of this kind of modeling. Now, we do that in a way through the safeguard mechanism and that declining baseline for not the whole industry sector, but a large subset of the industry sector. So in one sense, we have set a budget, but it isn't exactly a budget. It can be thought of in those terms, but each sector can be thought of as a budget, and how you think about how that evolves over time. And again, that point in the second one on the right is that we go to negative emissions sometime after 2040. There's one other little secret that's hiding in this that I want to, this will be just about my last slide, is that if you look at this slide and you ask me, well, how is climate change itself accounted for in this modeling? The answer is it wasn't. Not because we don't believe in it, not because we don't know it's happening, not because we don't know it's going to keep on happening for some time, simply that we don't have models configured to actually think about what the feedbacks are between these sectoral emissions and sectoral activities and climate change itself. Yep.
Is that just CO2 or is that all?
That's all greenhouse gas. That's CO2 equivalent. You see it says CO2e, so that actually is all of them. So, but again, you can think of it in those terms. Can I go to the next slide? So I just want to just highlight a few challenges that come up. There's some challenges. We have opportunities. I'm going to end on opportunities because I do want to be optimistic and positive, and we should be optimistic. I don't think we should be pessimistic. There's a lot we can do. One thing, and I just mentioned, techno-economic models not configured to incorporate climate feedbacks. So a good example of that is we said to move to a distributed energy system, electricity grid, we'll need a lot more high voltage transmission lines. Where will those transmission lines be? Will they be in areas of high bushfire risk or flood risk, or places that are likely to become areas of high bushfire risk? How do we anticipate and manage those risks? I said before, the shape of the pathway matters. And we need better ways of understanding the implications and the path dependencies, not only path dependencies in an Earth system sense, but path dependencies in a technological sense. Does the path matter and how does it matter? So we need to understand that. It's not easy to separate, in some sectors, deliberate actions from natural feedback. So this has been a big discussion in the carbon crediting world about how do you separate out your deliberate attempt to manage and get an ecosystem take up more carbon versus just what's happening in nature. And that's a challenge. It's very difficult to consider pathways to scale and economic viability for these emerging technologies that are essentially zero. Aside from just going around and asking people, which is what we also did that. But again, I think this is where ATSE could play a really constructive role in thinking about what is a credible pathway to scale. Also, the emissions implications of different mixes of technologies are not always, there's a lot of uncertainties because in some cases we don't really understand the full life cycle implications of moving to different technologies. You've seen this with examples of the embedded or embodied emissions in different products. Like, does an electric vehicle have more or less embodied emissions than an ICE vehicle? It's not always necessarily obvious. You need to understand the supply chains and where all the components came from, aside from the fact that, yes, the ICE vehicle will be producing operational emissions, burning fuels, and estimating what the residual is. What are we going to be left with is a really challenging question, because that is our task for removal. And I think that also, again, I put this out there because I'm talking to ATSE and I'm trying to spur you to help. One more slide, please. Look, we have a lot of opportunities. We have a lot of tech already in place that we can use. We need to scale them. We have a lot of low emissions energy resources. In some cases, as simple as sunlight. In other cases, a little more complicated in terms of geological formations into which we can inject and store CO2. And we have a lot of critical minerals. I think that's another challenge to actually not just find the resources, but build supply chains that take us from, digging a piece of ore out of the ground to a refined product. And we have policy architecture, things like the safeguard and the ATSE scheme that we can already work with, that are already, starting to work anyway. So I think we have a lot to build on, but we have these technologies, and I'll stop it there. And thank you very much for your attention.
Thanks to both of our speakers, Pep and Will, for talking us through from the fundamental science through to some of these policy and technical challenges and opportunities. I think to paint that picture and that overview in one package like that, I hope I certainly found that extremely informative. What I'm going to do now then, yes, thank you for both sitting there, is I'm going to go to questions. I will start in the room for the first one, just so that I can get a chance to check what's come in on the Q&A. So online people, I'll come to you in a second, but I'll start with the room and Ken first, and then we'll go to Brad. Ken.
So thank you both, that was really interesting. And I've got two questions based mainly around what Will was saying. So the forward trajectories that you showed in the last graph rely heavily on land use. And so my first question is, how many Amazon rainforests can Australia grow to actually achieve this? What land area limitations are you going to come up against? Particularly because you've got to keep planting each year and every year at least the same amount, because as the forest matures, its capability is diminished, right? So have you done a projection as to whether we'll run up against a land limit or even an economic limit to doing this? That's the first question. And the second question is, we talk a lot about carbon dioxide removal, but as you showed, don't forget, there are other greenhouse gases we need to worry about. Why aren't we talking about other greenhouse gas removals? Is it because of the atmospheric lifetime is shorter? Is it because we're not smart enough to work out how to do this? Why aren't we talking about other greenhouse gas removal?
And while you're thinking about who's going to answer what, can I check with Luke? Can online people hear people from the room?
Yes.
Do we need to come up to the mic?
No, they don't
to
need to
answer?
come to the mic.
No, they can sit at the table.
Okay.
I'm going to start, Ken, I'm going to start with both really good questions. I'm not sure I have complete answers to them, but I have partial answers. And the partial answer to the second question is people are working on technologies for things like methane removals. So there is some emerging research and development on that. But yeah, the reality is carbon dioxide is first of all, it is the biggest source of, methane is the next. So if you want to go after something, obviously, CO2 is the big control knob in the system, or the biggest control knob, but not the only one. But it's the only one that we actually have some technologies in place. There are technologies for CO2 removal through a range of liquid, solid sorbents. And again, the challenge is getting those to scale and getting them to both affordable money cost, but also energy cost. Direct air capture of like the plant that Pep showed, 2,000 kilowatt hours per ton of CO2. That's what they estimate. So if you imagined, like if you looked at one of our graphs up there, I think we had one where we had something like maybe 50 or 60. No, maybe we had one. Anyway, there are some scenarios where we end up with like 90% reduction from 2005. We end up with something like 60 megatons of residual emissions. So the arithmetic is pretty simple. 2,000 kilowatt hours a ton, that's 120 terawatt hours. That's half the current NEM. So there's a huge amount of electricity that you would need to remove that much CO2. So it's a serious scale challenge. And it's because the cost of CO2 removal is inversely proportional to the concentration of the stream. So even a coal-fired power station has a effluent stream that's relatively dilute. It's 10 to 15% CO2, and the atmosphere is 0.04% CO2. So those challenges are quite big. To go back to the point about the land, I think we are working on some of that question in another team, and trying to get some, again, credible estimates of what it would actually take. And it is a major scale challenge. And one of the big challenges is, again, the tension with other land uses. You know, food and fiber production, preservation of biodiversity. So there's a whole range of issues that, as you scale, inevitably, what you're doing is going to butt up against other things. I think those are the risks that we're probably most trying to anticipate. And Pep,
Just very,
something to add to that.
no, very short on the methane. I think you just said it. So it's a concentration. So we're talking about CO2 parts per million.
Yeah.
We're talking about parts per billion
Right.
in the methane. So the amount of energy that would require to do that is just triples, quadruples goes into order of magnitudes. The other one is that we've done some work, review work done. We identify some of these zeolites as a possible way to look at the conversion of methane into CO2. It's still very, very ridiculously expensive. You still need to capture air and push it through a system, a chemical system, and that's really the bottleneck.
Mm-hmm.
On the tree planting and all this stuff, an old assessment that CSIRO did, I mean, literally, there was the need for 6 Tasmanian sizes on reforestation to get to, I don't know exactly what they were getting to 2050. And there was all with, plantation species, which they're not, this is not the way we're gonna have a sustainable land sink or enhancement of the land.
Just on that one, just interrupt, but on the changing climate from the climate change scenarios, it basically says Northwest Australia will get wetter. So will that help in terms of vegetation taking off, for whatever better description? And it's almost on the scale that you're talking about in terms of 6 Tassies. But I mean, it's not in the system yet. It would be very hard to model, but it might be one of the beneficial outcomes from the changes that are occurring.
Yeah, it could. Again, but like some of the things that came up in some of our discussions were, again, supply chain. There are supply chain constraints. You might say, I want to plant this many trees. You need that many seedlings. That's
We're not doing the planting, just letting nature.
well, that's another point. But I think the point that Pep was making is that, nature giveth and nature taketh away. So that's a strong variability driver, and in Australia we know it's a strong variability driver for our land carbon sinks.
I'm going to keep us moving.
Yep.
And Brad, I'll get your thoughts. All right, we'll take yours, but then I do want to get your mind. So you go ahead.
I just wanted to make sure I understood how environmental or economic model works. Do you have like a cost curve for the different technologies, and you have a projected cost per ton sequestered, and then you just run it through an economic model that finds the lowest cost?
It is a kind of abatement, and there is an implicit economic driver within. I'm not the biggest expert on the G10 model, and this modeling was done. We did this with CSIRO, but again, the model does tries to solve and optimize for driving to a lower emission, and implicitly there is a cost in there, so it tries to drive to that. And that's another point that I wanted to mention about constructing scenarios that I think is poorly understood, because we've kind of transitioned from IPCC presenting us with open-ended scenarios. So the RCPs and SSPs have inputs, population, basically the Kaya identity, programmed into integrated assessment models, population, energy use, economic activity, and then let emissions go where they go and let a concentration profile or trajectory arise. Whereas now, with the indicative mitigation pathways, IPCC has brought in a different form of scenario, whereas you specify what you want the endpoint to be and solve everything else. And again, that's a very different way it's a different way of thinking about climate trajectory, and it's a different way of thinking about technology, where it's constrained by a goal. And I think, again, I think in the climate policy and science discourse, we haven't always been clear about what kind of a scenario we're talking about.
No, thanks.
Thanks, Brad. So I'm going to go to a couple of questions online. The first one, probably for you, Pep, but have we been able to quantify the permanence of carbon storage in natural sinks over, for example, 20-year lifespans?
Yeah, so basically, so there's now new tools emerging, particularly some of the satellite biomass tools that it gives an opportunity to actually do carbon stock change. That is all the carbon that has come in and how the net balance, meaning that anything that happens in between these 20 years, how much you had at the beginning, how much you have at the end. Of course, we model this thing routinely. Actually, we model the whole thing every single year. Models are models, but just to say that there's an emerging amount of data constraints, and I'm just giving you an example that is allowing us to do this thing a little better.
And there's a bunch of questions which I'm just trying to sort of synthesize, and they are all around afforestation and reforestation. Obviously, this is something that is of great interest to our audience. So I might sort of class these a bit. So the first one is, does the work include aquaculture? So kelp forests, mangroves, etc. When you're doing, I'm not quite sure the question when they say, does that work in reforesting and afforestation, but maybe Pep.
I'll just say a little thing. So we'll show the carbon budget of Australia. So we did it a few years ago. And for the first time, we made an effort to bring the whole coastal ecosystems as part of it to understand how relevant they are. Now, the only thing that we could do was to understand what's called the vertical exchange of fluxes. But we don't know exactly what's happening into the shelf and open ocean. So we cannot have a close carbon budget for these systems. Now we can look at the sediments, how the sediments have been accumulating over the last many years, and that gives you an indication about how much carbon can be sequestered. But you need to be careful because heat waves are increasing. Some of the stormy kind of types of weather are changing as well. And this is like going to the permafrost region and say, I'm going to buy carbon credits in the permafrost region because there's a lot of carbon that has been accumulating. Well, no, this carbon is not going to be here, in the coming centuries. So it's a difficult one, but it plays an important role, ecologically, a very important role. And yes, it takes a lot of carbon. We haven't done kelp. Kelp is even more difficult because kelp works with the storms, destroying a third, half of it, being washed into the deep ocean. There's estimates about what happens into the deep ocean with that carbon, but that's very difficult, very speculative. I would not put any money on a mitigation project on these things as yet.
But maybe it is at least some assurance to the person who posed the question that the science is very aware of the role.
Oh, yes, absolutely. And it's an important role. It's an important role.
And I'll just add to that, there is a lot of active work going on in a related issue, which is what's known as blue carbon.
Yeah.
That's carbon in coastal marine ecosystems, which includes things like the carbon in the sediments within mangrove ecosystems and seagrass beds. So it's a closely related space. But again, all those risks and uncertainties apply to those systems.
So as I said, there was about 3 around sort of area. So speaking of blue as in water, this is a question that I've got a particular sympathy with, so I'm being biased. Assuming that this is with reference to Australia, but what's with the afforestation work? Are there any studies looking at the impact on overall water tables and how the need for reforestation may or may not impact overall water planetary boundary issues? I think there's intersection between water and reforestation.
I'll say a word about water. So in Australia, water is carbon. So you need to decide what you cannot have it all. basically. So that's as simple as it is. What's the relatively role of the water, sorry, the rainfall versus the water table? But, basically you can have carbon and use the water that it's in the landscape, or you can have, more runoff and have less carbon and have more water. This thing has been well studied. We've modeled this thing very well for many years, going back to Mike Rappak and all those great scientists. And so you need to make a good regional assessment before you go big on any reforestation.
I'm going to do a follow-up to that one, and then I'll come back to the room from online. So this is now going back to your graph, Pep, where you showed the airborne fraction and the high variability from year to year. So given your finding around natural sinks varying quite dramatically from year to year, have we had to revise up our level of uncertainty around the land use change fraction into 2030, 2050? So it's actually almost, I think the question is about seeing what you've shown globally, Pep. What does that mean for our certainty or uncertainty for the land use change fraction?
Yeah, so I'll say something over to you, Will. So basically, so we're trying to model all these things. It's just that, how far the quality of this modeling is, it's a second thing, but, it's going to change dramatically regionally around the world. And again, back to Australia, really carbon and water, it's really a tight link. The other one is fire. And we've seen now how we talk about tipping points, and I've always been very skeptical about tipping points, but I can tell you we have identified a tipping point in the boreal region where 14 years ago, the continuation of what is an expected kind of climatological drying of the regions really started a very strong exponential growth in fire emissions to culminate in the 2021 massive fires in Siberia and 2023 many times bigger massive fires in Canada. So these things start making a difference, and these things begin to be real. Now, similarly, in 2003, we had this 1 in a century drought in Amazonia, and ecologists went just crazy about understanding what was going on and the impact of this thing. Since 2003, we had 6 major droughts in the Amazon, non-stop. And still this year, in our La Nina year, we have major drought. We can no longer explain. This thing is just not the old patterns of climate modes explaining what we see in some parts of the world. Now, back to Australia, of course, fire is very important, and we have identified a very clear increasing fire frequency over the last 20 years, very strong, the whole forested region of the southeast. Now, our vegetation is really tough, and it keeps cutting back and it keeps cutting back. There are limits to this. We haven't got to this limit, but if this thing continues this way, certainly we're going to get to limits.
Anything you wanted to add?
No,
Back to the room. Is there anything else burning?
Worth mentioning biochar, or is that dead horse? I mean, you can make biochar from agricultural crop residue and plant material and produce energy at the same time.
Right.
And it can be made permanent to work at.
We've been looking at that. No, it's not impossible. And there is small, but active industry in Australia. And there are a lot of co-benefits to the application of biochar for agricultural industries. It does have some advantages in terms of giving you a longer, a more refractory bit of carbon, more longer lasting bit of carbon in the soil. But again, we've looked at it, and again, trying to understand what a pathway to significant scale would be in terms of carbon removal is really challenging. As different price mechanisms come in, and the ACU scheme is a pricing mechanism of sorts. And so how you think about scaling different technologies such that, first of all, they're visible to schemes like that, and then competitive within schemes like that. That's from what we've been able to see, that's the challenge, just getting it to scale. Yes, it does exist. It has for a while. It's not new in and of itself, but again, it hasn't scaled. And there's a lot of supply chain issues around, what are you using for the feedstock? How are you treating it? But yes, it's got
Use stuff that bacteria would use anyhow.
definitely we've assessed it. Yes, it has a great deal of potential.
Oh, gosh, flood of hands. Peter.
Yeah, we've seen recently trends with Google and sort of high-tech companies saying we will no longer deal with carbon credits other than permanent carbon credits. What sort of level of uncertainty does that produce in the global carbon budgets if you start saying, well, 50% of the current carbon credits are actually uncertain? Or is it 60% or 5% or whatever it happens to be? If you start sort of putting that into your uncertainties when it comes to the global carbon project. I might just say one thing. I think your project is a fantastic project, and it's really, really important globally. And it's just great to see the level of support it gets here, and your particular contribution is really fantastic.
Thank you very much. So just to say that even the big corporations that they have been willing and making purchases at a $500 a ton of CO2, they're beginning to think twice about it. They're all over very excited, new technologies, they want to be there, they're technological corporations to begin with. And, it's progressing very slowly, and we know that it won't get cheap any soon. And there are alternative, mitigation, even if they're not that permanent, that are there. So we're not analyzing, as you said, globally, what's the level of uncertainty that's bringing into all these projections as you bring the less permanent thing. Because in part, the models are not doing well at these vulnerabilities. We don't have the resolution of fire frequency changes and regrowth capability that different biomes, different vegetation ecosystem types have around the world to be able to actually do this thing well. But that's what we need to do. That is the real deal. The real deal is not whether the temperature is going to be at 2 degrees more for a plant. It is really about, all these trigger points like wildfires that can actually change things very quickly. And you get to a point where, regeneration is not really occurring. And we see this thing in the taiga. So that's the southern part of the boreal forest, where some of the conifers that they burn are not coming back to conifer forest, they're coming back to a lower stature. That's still a small in the context of global, but is these type of things that, we expect that as we move into a much warmer world, we'll see more, and some of them happening quite quickly. And models are not capable to do that yet. Thanks.
I apologize in advance for this question. You're in a change of government, you've been put in the Minister for Environment's office as a principal advisor. And this minister is dead set on becoming the minister that saved Australia from the impacts of climate change. Where would you advise them to focus in the context of Australia? I've said I apologise for that.
Yeah.
It's a wicked problem, but we have to go step by step. So
Yeah. I guess one of the things that we've said as an agency, we're focused pretty strongly on the power sector. The reason for that is that a lot of the abatement levers that we've identified involve electrification of both residential processes, transport.
That appears to be underway, doesn't it?
Yeah, underway. And it's got opportunities, and it's also got some challenges. But a lot of that depends on decarbonization of the power sector, because that unlocks a whole lot of other opportunities. And again, it's got its own set of opportunities and challenges. The the falling costs of a lot of renewable energy technologies, of course, are a wind that's at our back. Supply chain constraints and the ability to scale some of these things quickly are challenges. So I'd say that is a big one, and I think there's some big challenges. I mentioned agriculture, and one of the things that you see in those graphs that I showed at the end is that the clear implication is that as other sectors decarbonize, the ones that remain more challenging will become bigger proportions of our overall emissions, and so everyone will be looking at those sectors. So I think like starting now, starting as soon as we can, or maybe 5 years ago, starting now to look at those sectors where there's some real challenges to decarbonization. Ag is one, and some of the very energy intensive industries which require things like high heat. They don't just need low grade heat. They need 800 degrees or 1,000 degrees. So those are serious. Those are real technological challenges to get them to decarbonize. So I guess if I had to say anything to any minister of any party, I would say, start thinking now about what all these sectors look like in 20 or 25 years.
Pep, would you add anything as the scientist advising Will?
Since you said how these ministers are going to spare Australia from these climate impacts, I would say you have to play a bigger global leadership role. And we're going to a big vacuum over the next 4 years. And we need examples, tangible, committed countries that they show the real progress. They show that they're actually making a relatively bigger effort than many other countries, and showcase this thing through leadership. And that's paramount, because as we know, whatever we do in Australia makes a little difference. It's on everything that needs to do to move into across anything that has to do with emissions.
And the only thing I would add to that is that, again, this is relevant to ATSE. Australia has a role to play in developing technologies that can be scaled and applied globally. Carbon capture is one example, but we've got a lot of others. So really, if you think about it, our challenge is not just to get our own emissions down. If we want to manage the impacts of climate change, we have to get everybody. So what's Australia? So our policy challenge really is, how does Australia get global emissions down?
The leadership.
To provide the leadership, provide some of those technologies.
And we actually had a couple of questions on that, and we're kind of running out of time to answer. I just wanted to let you know, so that people online know that I haven't forgotten, that one of the questions was, how much is Australia reliant on other countries' ability to scale down their CO2 emissions? And then the other bit goes to your Australian carbon budget, which you both showed. You showed, and it's Pep's work, which of course you're not taking exports, and what the plan is. So I guess this perspective about Australia in the world, have you got some closing comments on that? So exports and also our reliance on other countries.
Certainly, those exports, or what some people refer to as Scope 3 emissions, that is to say, we're a major exporter of coal and LNG. It doesn't count on our inventory, because those products are used and thus emit somewhere else. But it is, in a sense, part of the whole global climate change picture. And again, it's challenging to think about, how do you also sustain our economy? How do you make that transition to other forms of exports? Things like hydrogen, renewable energy. So there are other things we can export, in some cases do export, but making that transition technologically and economically, that's got its own set of challenges along with those opportunities. But it also means you need a substitute. I mean, think about what are other countries using those products for? They're using, for example, we're a major exporter of metallurgical coal. the world will still need to make steel, even in a renewable, even in a system. In fact, we may need to make more steel. So how do we help other countries transition from that major use of metallurgical coal to either alternatives that have low or no emissions? For example, can you apply economically carbon capture to steel making? And people have been working on that too.
Just to say that actually our carbon budgets do take into account all the trading. And I encourage you to look at the actual Australian carbon budget, which the single biggest area, of course, was the traded, fossil fuel. So yeah, we do take advantage. When you do globally, it doesn't really matter. When, of course, you go into regions and nations, is when this thing becomes very relevant. How this thing gets solved, the convention has made decisions about how they want to deal with, who is responsible for what. And that has been agreed, and that's the way we go with. I'll say that the import component, not the fossil fuel, but the green energy, I think that thank goodness, we are relying tremendously, and the globe will continue to rely tremendously on green technology from China. And that's very important. The only issue has been is that it's disproportionate now as one single source of green technology being exported around the world. 70% of the investment globally on green technology is in China, which basically means that we need to diversify a little. But thank goodness we have, China to really supply at a more affordable prices a lot of the technologies we do, not just because they're cheaper, it's just because they're available, and other industrial countries have not gone and begin to produce the quantities that we need, from hydrolyzers to electric cars, you name it, which are being supplied out of China. As you said, we need to rebalance a little the global, sources of this technology, but, it is a very important part of our decarbonization plan.
Sadly, we have run out of time. I feel like we could keep talking about this for a long time, so I'm sorry to people online who didn't quite get their questions answered. But I'd like to say a couple of things in closing. Firstly, I hope you would agree with me, audience, that I can't think of almost two better speakers in Australia to take us from this underpinning science through to the challenge of setting policy. So thank you both. You've really, I think, painted such a clear picture. I also want to thank Pep and his role in the Global Carbon Project. As I think one of our audience members here said, it's such fundamentally important work. So thank you for that. Thanks, Will, for your last slide, which I will steal from what ATSE. I really hope that ATSE might be inspired to think a bit more, and I'm part of a cross-ATSE working group, and Ken's on the same working group. We're thinking about how we can add value here, so that kind of pointer and direction and inspiration is really much valued. Thanks for explaining to us the role of the Climate Change Authority. I think that's important. Good luck going forward. I know we're in challenging times. And thanks, audience, for your engagement and great questions. And any feedback around today or what you'd like to see for our ACT division in terms of these kind of presentations, contact me directly or Luke at the ATSE Secretariat. We're always keen to hear from you. So thank you once again for your time, and thank you, Pep and Will, for two great presentations. See you next time. Oh, and I meant to add, there will be some communication soon, probably through March, about the next of these hybrid seminars. So keep an eye out for those.